Hello, everybody. My name is Paul Gazzillo, and I'm an assistant professor of computer science at the University of Central Florida. Today, I'll be presenting inferring and securing software configurations using automated reasoning. Highly configurable software underpins much of our computing infrastructure. This is because configurability enables extensive reuse without having to reprogram the software for a particular device or application. The Linux kernel and the Apache webserver are just two examples of this highly configurable software. The Linux kernel alone is used in billions of computing devices, and the Apache webserver is used in a large proportion of web servers. Their extreme configurability is what makes this widespread use possible. But this configurability has a downside. It introduces the potential for misconfiguration vulnerabilities. Misconfiguration vulnerabilities happen when some combination of configuration options reveals a software bug or an unexpected combination of software components or just security holes due to bad settings. This may be something as simple as failing to change a default password on a router, which is how the famous Mirai botnet was able to spread. A particularly extreme example was a privilege escalation exploit in the Linux kernel due to a dangling pointer. And what was interesting about this exploit is that it was possible on different distributions of the GNU Linux operating system. Ubuntu distributions were vulnerable, but Debian distributions were not, even for the same architecture and even using the same kernel version. And this was because the exploit depended on a particular configuration option to be set that allowed the user to read log messages from the kernel. In fact, the OWASP Foundation lists misconfiguration vulnerabilities in their top 10 most critical security risks, and they're even the most commonly reported one. Now, program analysis and verification and testing techniques have had really good success in catching software bugs. What makes misconfiguration vulnerabilities such a challenge is they aren't quite like traditional software bugs. While program analysis techniques generally focus on the source or object code, misconfiguration vulnerabilities are rooted in software configuration management. Now, software configuration management is a very broad term that encompasses any change in software and the control of that change. Now, this includes change at every stage of the software development lifecycle. But for misconfiguration vulnerabilities, we're most concerned with changes that occur after development. Developers include machinery to allow this kind of post-development change so that users can customize their software without having to go back and redevelop the software. But what we end up with is endless variations of the same piece of software all contained in the same codebase. The vision is a world without misconfiguration vulnerabilities by automating the creation of reliable and secure configurations. In this way, the burden of getting software configuration right is not on the user. The key to this vision is to take the techniques and tools from formal logic that have been developed for program analysis and use them to model problems in configuration management. In this way, the validity of a software configuration is equivalent to the problem of satisfiability. But there are two key challenges standing in the way of this vision. First, real-world software systems, even those that are well-maintained and high quality, often lack a complete explicit specification of what configurations are valid. This is one reason why hardening guides exist, even though they aren't really recommended for use by security experts. They can go out of date quickly, they may not be comprehensive. But without some way to capture these specifications, we can't apply automated reasoning techniques. The second challenge is that even if we can capture configuration specifications, the space of possible configurations is enormous. For instance, the Linux kernel alone has about 14,000 configuration options just for its x86 version. And even though most of these are basically Boolean on-off choices, that's still about 2 to the 14,000 possible combinations of configuration option choices. To use a cliched analogy, that's more than the number of atoms in the universe. So a solution that can overcome these challenges needs to be able to do a few things. We need some way to rigorously define what configuration specifications are, and ideally have some way to collect these specifications from real-world software, ideally as automatically as possible. Then we can use formal methods to mechanize the validation and generation of the configurations for the particular piece of software. Finally, we can take this mechanization a step further and use it to discover configurations that satisfy the security properties that we're interested in for the software. Let's take a look at a misconfiguration vulnerability that happened in the wild. Optionsbleed would bleed or leak memory contents of an Apache web server to a remote attacker. And it was due to a use after free bug in the code that handles restricting the use of HTTP methods. And it would only happen if a user provides an invalid configuration file that references non-existent HTTP methods. Without a mechanical check, this invalid configuration just fails silently. The limit directive restricts access to HTTP methods in an Apache web server. And this is really useful for locking a web server down. But this file contains a misspelling of the delete method. And it turns out that this misspelling leads to the use after free vulnerability, where an attacker can remotely exploit the server to give it chunks of server memory. And this limit directive can be added to an unprivileged configuration file on the server. Now, this is just a simple misspelling, easy to catch with some string pattern matching. But let's take a look at this bind method. The bind method can be a valid method sometimes, so you wouldn't think it would trigger an optionsbleed vulnerability. But the bind method is not actually part of the original HTTP protocol. It's only part of an extension called webdav, which adds some file system-like behavior to the HTTP protocol. And as it turns out, the Apache web server gives a system administrator control over whether the webdav extension is part of their web server. And there are actually two separate mechanisms involved. First, there's a configure script that controls whether the component is ever even compiled. And then there's a module system for loading and unloading these components for the runtime system. So the question of whether bind is a valid method depends on both the compile time and runtime configuration of some particular web server. And that means the question of whether this same limit directive triggers optionsbleed or not has nothing to do with the limit directive itself, but it depends on how the web server was configured and built in the first place. Bind triggers this vulnerability only if the webdav extension has been disabled, either at compile time or runtime. And now, even though this complicates the validity of the limit directive, this kind of configurability is a good thing because we don't want bloated systems. If a web server really has no need for this extension, there's no reason to waste precious memory space on unused software components. And it's a good thing for security because less bloat means a smaller attack surface. Reducing the attack surface is a key property for secure systems. In this case, however, keeping the attack surface small by configuring out webdav ironically increases the possibility of triggering optionsbleed, because it's hard to tell just from the limit directive itself whether the methods it's limiting is valid or not for some particular web server. The solution approach is to automatically validate and generate software configurations. If we take this approach for the optionsbleed vulnerability, we can see how automated reasoning can prevent invalid configurations that trigger optionsbleed. Here we have the three mechanisms that implement configurability, and we can record the constraints on their legal usages using a logical formula. For instance, the bind method is only legal if both the build system and the runtime system enabled WebDAV. So the solutions to this formula define what configurations are valid, and we can use Boolean satisfiability to ensure that only valid configurations are generated. Applied to the Apache web server, at least conceptually, this rules out the possibility of triggering optionsbleed. And so this is a line of research that me and my students are working on to make this happen, and there are several research tasks that we're undertaking in order to achieve this goal. The first is to design an intermediate language so that the specifications from separate configuration mechanisms can be combined in a unified format. To be useful in the real world, this task also includes strategies for extracting these automatically or semi-automatically from real-world configuration mechanisms like makefiles, for instance. The second task is to take this intermediate language and compile it to formal logic with an eye on ensuring scalability. So if we can take advantage of the modularity in configuration systems, for instance, Apache web server has several different components to its configuration system, we might be able to make the automated reasoning more efficient. So third, we're looking at testing approaches to automate bug finding. And so these strategies search the space of possible configurations for vulnerabilities. And lastly, we're looking at automated techniques to find and discover specifications that ensure security properties that we're looking for. So please take a look at the paper for more discussion of these areas and references to some of the work in progress that we already have. So that's the end of my talk. Thank you so much for watching. I hope you enjoyed it, and I look forward to any questions or feedback that you might have. Have a good one.